Great, awesome. Well, thank you. Thank you for the awesome introduction. Thanks for having me, guys. Actually, why don't we go ahead and give a round of applause to Lexi and the organizers for putting on one of the best conferences in the Bay Area. Thank you, guys. So today I want to talk a little bit about how to get some level of interpretability out of your models and how to understand what your model doesn't know with variational methods. And I think interpretability is one of these things that divides scientists in academia from scientists in industry. I think when you're deep inside of machine learning and deep learning, you become focused on that benchmark, and the first thing to go is interpretability. And I think that's the wrong approach, right? And I think that's especially the wrong approach in industry. I think academics tend to focus on the science of algorithms. What are my bottlenecks? What are my abstractions? How does convergence working? How is regularization working? But in industry, the value is in the data, and the algorithm is the tool just to extract value out of that data. So instead of the science and algorithms, I'm actually very, very, very interested in using algorithms to do science. So this talk is about how to do that and understand what your model is doing, and also reason about what your model doesn't know. So my name's Chris Moody. It's my Twitter handle. I went to Caltech, did physics, did a lot of supercomputing back in the day. Scikit-learn contributor, a chainer contributor, and I'm starting to move over more into PyTorch land. Aside from deep learning, I also really love things like Gaussian processes and tensor decomposition. So if that's up your alley, I'd love to nerd out about that stuff as well. So at a conference about 2 weeks ago, Brendan Frey, who's the CEO of Deep Genomics, is a startup trying to solve health problems with deep learning, said, we have the full genetic code. What's the problem? Can't we just look at it? Of course, he was saying this rhetorically. And of course, this audience is going to understand what the problems are with that stuff, right? It's going to be big data. You're going to have all these weird patterns inside of this stuff. It's hard to do causal inference on just that data set. But one thing that stood out to me from what he said there, and it was that you need to be able to trust your model, right? You need to be able to break that model into components that humans can actually understand. And that's a desire that's present in every human enterprise, from healthcare all the way down to fashion, which is what we're doing at Stitch Fix. And so I'm going to talk about 3 different things that will help you understand what your models are doing. One of them is t-SNE, the second is a KSVD, and the third is going to be LDA-DVEC, if we actually have time to talk about that. And to start with, while this talk is super general, I'm going to start with a very specific example just to get us kick-started. And this is going to be a very, very simple co-occurrence model, and it's going to be off in NLP land. And I like it because NLP can be this sort of messy affair, because you have to teach a computer about the irregularities and the ambiguities of the English language. And as a result, when you actually find a model that works, it can be extremely gratifying to the scientist, and it can be really useful to the business and application. Right? And so this is a client comment about a particular item, and I've artificially injected this token, item 92, in front of it. And that token looks a little, that item looks a little bit like this. And so the client's written, I think this fabric is wonderful. It's got rayon spandex. I really like the lace and embroidery accents. And all of deep learning is running this sort of text, sort of co-occurrence model behind the scenes anyway. So this is just going to be a really simple bag of words baseline on top of it. And it's going to give you, but the important part is it's going to give you vectors that aren't immediately interpreted, and we're going to try and interpret it after the fact today. And so this is a model is nice, and it's going to embed both words and items in the same space, and we're just going to start off by counting, right? So we're going to count how many times did item 92 show up around the word spandex, think show up around the word spandex, how many times did fabric show around spandex, and wonderful, and rayon, and so on and so forth, all across some number of words before that word and some number of words afterwards, some window around it, right? And so we're just counting up pairs of words around the word spandex, and we're putting them into my little matrix X. Great, and we're going to do that for the word like, and we're going to do that for the word lace, and embroidery and accents and so on and so forth. So X is just this 2D matrix where each element is just the count of how many times I saw that pair of words near each other. Fine. Right. So far super easy. It's a minor modification from things like glove and word-to-vec-like algorithms. I'm going to take the log of that count because words are log distributed, and I'm going to break it up into 3 little pieces. One of them is going to be how frequent that first word is. So if I have a tuple like and embroidery, and I count how many times like showed up around embroidery, maybe that pair of words is really high, has a really high count just because the word like is a really, really frequent word. And there isn't any sort of special relationship between the word like and embroidery. It's just that like is a common word. So that first term is accounting for that. Second term is how frequent does the word embroidery show up? And then the third term, that's the most interesting one. That's going to say, is there anything special between the word like and anything special between the word embroidery? If so, the dot product of their vectors is going to be a little bit higher. If not, the dot product is going to be a little bit lower. So things like and embroidery, not that related. But words like spandex and rayon, both materials show up in the same sort of items, show up in the same sort of context. Well, they're going to be similar, and their dot product and their vectors are going to be similar, and they're going to push up those counts up a little bit higher. So anyway, so this is a super simple model to implement. But I want to take a moment just to have a little call out here. Stitch Fix is very heavy into NLP and very heavy into recommendations engines, and I want to draw out this similarity just for a moment here, that this is exactly the same sort of model that won like the Netflix prize, right? So it's some matrix factorization approach, except instead of saying how popular is the word like and how popular is the word embroidery, I'm saying how frequently does this user like buy stuff, how frequently is this item bought, so sort of just the marginal probabilities of those things being bought, plus interaction between those two things. How similar are the words rayon and spandex? How similar is this user to this item? Same sort of model, very different applications. All right, anyway, so you can pop this into like whatever your favorite gradient descent framework is, right? So it could be PyTorch, it could be Chainer. Hell, even Vopal Wabbit will actually do this for you with a few command line arguments, right? And in fact, this actually also is really, really similar to what fastText is doing too, if you supervise this model and also add a hash trick. So this is a really nice way of thinking about a lot of different models. Anyway, so if you have a lot of time, this can actually take a lot of time to converge. And back in the day when I was first doing Word2Vec, it would actually take days to converge, and now with GPUs it's a little bit faster. But if you actually just take the SVD of this, you can get the same answer in 10 minutes. It's the same answer every time with no fuss. You can do it on one CPU with limited memory, and it's fantastic, right? So you can take the SVD of just how frequently those two words showed up together. That was my X matrix. Divide by how frequent those individual things are. I take the SVD of that, I get deep learning quality results, right? So this is this Yoav Goldberg paper and Levy-Omer paper that say, this is a really simple way to get word vectors out. No neural networks, but I can be done in 10 minutes on a simple CPU with vanilla like linear algebra libraries. You know, vanilla like SciPy and NumPy will totally be able to do this for you just by counting stuff up. Okay, anyway, so random aside, whatever. I've built up my model, I get my tokens, I get my vectors. I may have solved it with SVD, I may have done it with a gradient descent, whatever. My vector looks a little bit like this, it's a bunch of numbers, and there's no way I can actually start to understand these numbers until I start like building a model around that too. You know, maybe I'm doing an image thing, in which case maybe you're thinking about vectors in images. Maybe you have like, maybe you've run a document model, you're thinking about vectors for documents. But like, let's just go back to like our words model, and like, let's start by looking at what the nearest neighbors are for each one of those things. So for the word spandex, it might be that the nearest token is stretchy fabric. Great, awesome. Spandex, totally a kind of stretchy fabric. If no one knew what the word spandex was, I would totally describe it as a stretchy fabric in some way. Great. But this is still like a very local view of what my model is doing. It doesn't really give you a sense of scale of what your model is doing. And so this is something so TSNE is a way of actually sort of getting a global picture of what your model can actually do. So this is a picture of all of our styles as our clients describe them. And what we're doing at Stitch Fix is we're actually selling artwork. So I'm really not interested in how it's categorized inside of our internal database, right? It's art. Like, there's no way that some random columns are really going to describe how our clients internalize it. So I'm really, really interested in that internal description of how those clients describe our styles. Anyway, so this is TSNE. This is students T distributed stochastic neighbor embedding, which is a total mouthful. But what it's actually doing is it's explicitly modeling pairwise relationships in that high dimensional space. So this is very different than things like autoencoders, PCA, and dimensional error reduction techniques, because those things are trying to rebuild and reconstruct the original signal. TSNE is not really interested in doing that. TSNE is trying to reconstruct the pairwise relationships between points. And it does that by doing kernel matching. It has this high dimensional input kernel, says how far apart are these two pairs of points in a high dimensional space. Well, that should be that should be very analogous to how close they are in this two-dimensional space and exactly on that plane. With funny definitions for what distance means and for funny definitions for how to actually compare distances. But again, it's all about the pairwise relationships, not the actual input signal. Anyway, let's look at a patch of space. Here's one that's like devoted to just scarves. Here's another that's like just jewelry. And you can see this thin, dangly jewelry on the lower left, and it's going to pendants and statement pieces up towards the top. Here's another piece where it has summer dresses, maybe color blocks towards the upper right. Now, there are problems with TSNE though, right? And so this is Neil Lawrence, and he's one of the, he's probably one of the biggest minds behind Gaussian processes. And as he put it, you know, nonlinear methods are like drinking whiskey straight, not for the uninitiated. So here's what he's referring to. I wouldn't blame you if you thought that this distance right here was actually twice the distance as this right here. But you'd be wrong. That distance is completely meaningless, right? That global structure is completely lost. There's also a bunch of other problems with t-SNE. The random noise in here might not be random. There's all kinds of strings and random shapes that might form. There's no categorization. So a lot of this stuff is kind of like reading tea leaves. But there are some tantalizing details here. I can look at this patch of like skinnies, and I can move up towards the top left, and it starts to get more exotic sort of skinny genes. So it does seem to have some local structure in it. If I can move and look at these genes, as I go up towards the top, I get more colorful things. As I move to the bottom, I get lighter genes. And so for me, this is the holy grail, right? Learning these directions, they tell me how to characterize my business. This is how our clients see my business. And this is what it means. But at the end of the day, what I really want is, how do I actually read these tea leaves? Are they actually real? Now, we get hints that these directions do exist outside of t-SNE, right? So if we go back to word vectors, this is obviously the very famous relationship between man and woman being the same thing as the difference between king and queen. Same consistent relationship across aunt and uncle and daughter and son. And this is when we talk about linear regularity, this is what we're referring to, that direction always means it's like the more feminine axis. And of course, we have hundreds of other directions encoding hundreds of other ideas. There might be a status direction, right? To me, those are the directions I want to find in my model. Now, we're probably not capturing status and gender since I'm on a clothing data set, but what are the directions that we're capturing? What are the interesting directions in my space? t-SNE is scrambling most of the directions, only keeping these local deviations, but what are the key directions in my space? And now, this is generic. If you think this is just for word vectors, you'd be wrong. This is actually generic across a lot of different models. If you're looking at faces, there's a really awesome Twitter bot called the smile vector thing, which would automatically take an input image and add a smile vector to it and slowly make it smile more. So these kinds of directions exist, and it happens in models where the latent space is distributed under the dot product, right? And that's what's forcing these linear regularities in the latent space. Anyway, this is where the KSVD comes in really, really handy. So this is another trick from the old world that brings interpretability in a really useful way. Before the KSVD, my CEO would come up to me and say, hey, Katrina would ask, what are our clients saying about this particular style? And I would just hand her back this dense vector, and she was like, what am I paying you for? There's no way I can actually do anything with that vector. But after the KSVD, it'll actually return you back saying, it's plus 0.53 in atom 23 direction, it's plus 0.16 in atom 95. Now, atoms in the KSVD are basically the same idea as eigenvectors in SVD, components in PCA, factors in NMF, topics in LDA. KSVD just calls them atoms, but whatever they are, they're just directions in this space. So you can think of them like my feminine axis or my status axis in Word2Vec. Now, with a little bit of elbow grease, I can figure out that atom 23 is really like the tank top atom, and atom 95 is really like the exposed shoulder atom. And you figure that out by looking at what else was really big into atom 23, and what else was really big into atom 95, and I figure that's it's tank tops and exposed shoulders. Atom 1 is all about dresses. Atom 40 might be sort of this urban and bohemian atom. Atom 22 is about statement pieces. Atom 75 about ring and drop earrings. So to me, this is great because I start discovering a lot of directions that live in that space. And I would highly recommend checking out this blog post, which is on the bottom left-hand side here, of decoding the thought vector. They push this technique into all kinds of sentences techniques, all kinds of other image techniques. Super interesting stuff. I don't have a huge amount of time to talk about LDA2Vec, but LDA2Vec is another way to actually build sparsity into your models and learning about not just word-word co-occurrences, but topic-to-word and document-to-word co-occurrences. And the really nice thing is you get visualizations like this where you can learn what the topic space actually means. Critically, though, instead of being plus 0.53 in atom 23, you're now 90% in the tank top topic. And instead of being plus 0.9 whatever, you're now 10% in the topic. So the sparsity constraint is that everything has to sum to 100% instead of just being positive or negative. Anyway, so this is an interesting way to add interpretability and sparsity to your model. All right, so now I really want to talk about variational methods. These are really, really exciting techniques that you can add to your machine learning models. So most machine learning, most deep learning is about optimizing a point estimate on your model parameters. If you've never seen a client, you should probably be really, really uncertain about that client. This is a way of doing this. You can have alternative modes of regularizing your model. You can think of this as an alternative to things like dropout. But it has very, very, very practical implications for things inside of a business, right? So if you trained a model that's only seen images of, say, denim jeans and never seen any jackets, well, when you see a denim jacket, You should be certain of the material, but maybe uncertain about like the category and department. And variational methods are a way of applying that sort of idea within the rest of your model. Now, what's interesting is that these things are actually extremely simple to like very little effort to write code for. These methods will totally fit in a tweet. And just in case you don't believe me, here's like a whole tweet that will actually do variational inference for you in just a few lines of code. This is using AutoGrad, but it's not very different in, say, something like PyTorch. And I want to take a moment to take the next few minutes to unpack what's going on here. So let's go back to our favorite model over here, very simple variational word vectors. And we're going to make it variational, right? And we're going to do it in two steps. One, by replacing point estimates with samples from a distribution, okay? And then we're going to regularize that point. Instead of regularizing that point, we're actually going to regularize that distribution and say that distribution should look really, really similar to my prior. And we're going to use a little bit of PyTorch code to do this. Great. So if I wanted to rip out that one vector corresponding to the word style, to the word like or word embroidery, this is how we do it inside of PyTorch. I declare one matrix of word vectors, and I pull out a particular row out of that matrix at a particular index, and that row is going to be my word vector now. Super simple to do in PyTorch. And now here's what it looks like with the variational mode, right? So now I'm going to have a mean vector. I'm going to have a log variance vector. So instead of one matrix, I now have two matrices. Instead of one vector, I have two vectors. And what these two things are doing is that they're parameterizing one distribution for me, right? So that vector mu and that vector LV, well, that's going to set the mean of my distribution. If that vector is a little bit larger, it's going to shift that distribution to the right, at least in this figure. If that log variance is larger, it's going to make that distribution fatter. If that log variance is smaller, it's going to make that distribution skinnier. And I'm going to take samples from that distribution, right? And it's going to be stochastic. So every time I run this, I'm going to get a slightly different answer. It's no longer going to be deterministic. And this is going to allow us to get a different sample every single time. And every time I backprop through this, it's going to affect both my mean and my variance. So in contrast to networks before, which were just pushing one point around, I am now pushing a whole distribution around. Now, the cool thing is up until 2013, doing exactly this kind of math and algebra required all kinds of formidable integral tricks, all kinds of specialized math. If you look at like the LDA paper way back in the day, which is solved using variational methods, it's incredibly impressively, it's an impressive feat of like variational calculus. You don't need to do that anymore. This is a beautiful reparameterization trick, and it unifies a lot of approaches, and it's at the core of Bayesian deep learning methods. And what's more, it's super elegant, right? It didn't have to be elegant, but it was, and it can be implemented in Python code fitting inside just a few lines right here. Okay, so fine. I've replaced my point with samples from a distribution. Now I need to regularize that distribution and say that distribution needs to be really, really similar to my prior, for example. Without the variational method, you would probably just penalize points just by, for example, penalizing the L2 norm of something. I take that vector, I square it, I sum all the components. This is basically saying that this needs to be as close to 0, and it needs to compromise between 0 and how much data I get. But now we're playing not with points and not with parameters, but with distributions. And the way that I compare two distributions, among many different ways, but the one that is usually approached in variational methods is by compare them by using the KL divergence. And what this is going to do is it's going to say, hey, look, that mu and that log variance, that needs to be pushed towards my prior. So if I'm off to the left of my prior, it's going to push it a little bit closer. And if my if my mu and log variance are very far away to the right of that prior, it's going to push it more towards the left. Okay. Let's bring this back into reality, and let's try to understand what's actually going on here. If I trained my point estimate word vector model, I might get this kind of relationship back, right? So I get king and queen, man and woman, but also have this really weird extra matrix hanging around that's describing the variances around each one of these points. What does that actually mean? Well, it's a variance, so I can start to visualize it, and it might look like this, right? So instead of points, I now have ellipses around this stuff, and this is now describing a probability distribution for the vector for the word man. And it's interesting, right? So right here, that ellipse for the word man is much, much larger than it is for a woman, for a king, and for queen. And why is that? And it's because the word man here is used in a bunch of different contexts. It can refer to being a human male. That's definition number 1. It can be referred to like human beings in general, right? So like mankind. Or it can be used like sticking it to the man, so like being a general like authoritative figure. So the word vector for man is actually used in a lot of different contexts, and the variational vector around that is trying to capture that. So it's not just the average, it's not just the point estimate of it, it's actually being used in a lot of different contexts. So in this case, I think of this as a very powerful idea because variance is no longer just a regularization technique. It's no longer just measuring noise. It's actually telling me what my model's claims is consistent with my data. And this variance is not just uncertainty, it's actually giving me a new kind of representation with novel properties. So this you can also see this in like the word to Gauss paper. You can take the vector for Bach, and you can see that it's actually within the vector for composer. So it entails composer. Bach was a composer, totally makes sense. It's within the vector distribution for classical, and it's within the vector for math, right? So now we're not just capturing similarities anymore, we're actually capturing linear regularities and all kinds of entailment, and the property that words can actually be subsumed entirely by other tokens. And so this is something that the original WordDevec didn't have entirely, and this is an example of learning hierarchical representations by by understanding that these word vectors can exist in a lot of different places all at once. Okay. So a lot about word vectors here. Let's try it on something totally different, right? So this is an experiment that I was working on the last few days. You all are the first to see this, aside from like a few Twitter people, so take everything I say with a huge grain of salt. On the left-hand side, I'm going to turn on the movie in just a second, is a traditional point estimate of t-SNE on raw MNIST pixels. So no deep learning, just looking at the raw pixels. And on the right-hand side, it's exactly the same data set, but I'm going to use a variational form of t-SNE. So I'm going to start in just a second, but I want you guys to notice from the get-go that the ellipses on the right-hand side are huge, right? So my model is very uncertain about where these points should be. And as we start to evolve the whole model, like you'll see those ellipses get a little bit smaller and smaller and smaller. And so that's the model's way of expressing its confidence, and of estimating its own confidence and expressing it back to you. And you can see that those in the variational model, those points are migrating. When they're migrating, that those ellipses are a little bit larger. And it's a way of saying that I'm really not sure about where this point should be. That's really useful because things like t-SNE have all kinds of reading the tea leaves behind it. So knowing where those points actually are is super useful. So you can always end up in this kind of case, right? You can end up looking at if you're looking at the left-hand side here, if you look at that point that's all the way up at the top left, and it's not near anything, I certainly look at that and I say, is that a real point? If I reran t-SNE, would that thing not be next to anything else? I don't know. Anyway, so you run this thing, and both t-SNE and variational t-SNE will converge, and at the end of the day, only the variational model is going to have a disciplined measure for its confidence, right? So if we can let's see if I can actually zoom in on different parts here. Right, so over here, this is a huge ellipse. Maybe I'm not actually very certain about that point. But there's points that are going to be farther up in different parts of this space that I'm going to be extremely certain about. I'm not going to be certain about any of the points over here. Sorry, this is really hard to do when I can't actually have the same screen on my own laptop. But having that notion of what to be confident about, what not to be confident about, is how I build trust in my actual model. And it makes it feel like I'm reading the tea leaves a little bit less. All right, so anyway, so you guys have been an awesome audience. If there's a few things that I want you to take away, it's try using SVD form instead of the neural network form of WordDevec. Try using t-SNE, although I think everyone already is pretty familiar with t-SNE. Try using the KSVD to interpret your model. I think this is very rarely that have I ever seen a paper actually use the KSVD. And try variational methods when it's important to know what your model doesn't know. Okay, so that's my Twitter handle, Chrissy Moody. I'll actually be talking about a bunch of different stuff coming up. We're going to try and apply nuclear norms, which is a way of building sparse representations for matrices, and try thinking about them in the context of things like LSTMs, which are sort of notoriously uninterpretable. Anyway, sorry, I've gone on far long enough. You guys have been an awesome audience. Thank you very much. I don't know if you have time for questions or not.
Oh, we do.
Oh, great.
How would this be modified for next nearest neighbor associations rather than word pairs? And how would that look in this sort of t-SNE analysis?
In fact, like when you look at, so let me see if I actually understand the question. How would this be modified if you looked at just nearest neighbors?
Next nearest neighbors.
Oh, next nearest neighbors. Yeah, so if you look at a lot of the original t-SNE papers, it's a little bit difficult to actually measure how good a job t-SNE is doing because it's an unsupervised problem. But one of the metrics that they use is how faithfully is the nearest neighbor in this two-dimensional space reproduce the nearest neighbor in the high-dimensional space. And they ask that not just for the nearest neighbor, but like the next nearest neighbor and so on and so forth. And you can see that t-SNE does a very good job of reproducing the nearest neighbor graph very, very well.
Any more questions? Thank you very much.
Cool, thank you guys.